Hello, good morning everyone. This is Saqti Mohanty, and I am today we are having a discussion on applied physics, and we will be discussing a part of applied physics that is a part of modern physics, and that leads to a bit of quantum mechanics. And the discussion is basically on Compton effect. And all of you know a little about Compton effect, you have heard of it a bit. But let me try with all of you know that light has dual nature, wave nature and particle nature. If you look at wave nature of light, there are different phenomena explaining wave nature of light. Like phenomena like interference explains wave nature of light, diffraction, polarization and other effects are also there explaining wave nature of light. I will be discussing just one lines for each phenomena before going to Compton effect. Interference is related to wave nature of light, and basically all of you know that light plus light can be brightness, light plus light can be more light or brightness, but surprisingly light plus light can be less light, can be dim effect, and surprisingly, more surprisingly, light plus light can lead to complete darkness. That is the basic idea of interference. Come to the second one, diffraction of light. And in diffraction you find there is a spreading of light through a narrow slit, or you can call that bending of light about an obstacle. That is what a bit of diffraction is. And you also have heard of it, polarization. In polarization there is rotation of light or twisting of light about an axis, a little bit of that. But come down to particle nature of light. In particle nature of light we have different phenomena explaining particle nature of light, like we have Blackbody radiation, photoelectric effect, pair production, Compton effect. So, these phenomena explain particle nature of light. All of you know about Blackbody radiation, very popular, all of you know this. When light falls on an object, there are different options like RAT, R-A-T, RAT. A part of light is reflected, a part of light is absorbed, and a part gets transmitted. Out of this RAT, a black body or a perfect black body doesn't do this, it absorbs the total amount of light falling on it, or you can say that the absorptance of a perfect black body is 1 or 100%. Photoelectric effect, all of you know one liner for photoelectric effect, that there is a metal plate, light falling on it, electrons are ejected out of the plate, and they lead to a current that is called photocurrent, that is also about particle nature of light, photoelectric effect. And in pair production, that is really a very interesting phenomenon, pair production. You have gamma ray photons passing closer to a nucleus, and as a result two antiparticles are formed, one is electron and one is positron. And pair production, as an introduction, is a phenomenon in which there is energy converted into matter. But our discussion, today's discussion is about Compton effect. We are talking about Compton effect as today's discussion. Let me brief what Compton effect is, then some mathematical aspects of Compton effect, then some graphical discussion, and then the physics or the application of Compton effect. So, looking at Compton effect, I will give you an analogy of Compton effect first to have a clear idea. First, all of you know that Compton effect is about particle nature of light, and Compton effect is like a scattering phenomenon. It is a scattering phenomenon or it is a collision. just like you can think of a 2D collision, two-dimensional collision. Imagine that you are playing carom, and on the carom board you are playing your favorite shot, that is a cut shot. What do you do in carom? Your dot is here, the carom dot is here, and you are using the striker, is the striker, and when you play the cut shot, the dot is scattered to one of the pockets of the corner, and the striker is again scattered to another pocket of the corner. So, this is a little scattering effect related to Compton effect or Compton scattering. But what we do in Compton effect? We also have two particles colliding with each other, and these two particles are, one is electron and the other particle is photon, because you know that photon are the light particles or the packets are called photons. So, a photon is colliding with an electron to give us this Compton scattering effect. So, what is there? Which photon we choose? Experimentally, it is very evident that X-ray photons suit the Compton effects better. So, we have a collision of an electron and an X-ray photon. Why X-ray? Because any photon can do this effect, even if visible light can do this effect, but X-ray photons are practically, experimentally, they are more visualized, more evident. That is why we choose X-ray photons experimentally. So, in Compton effect, we are having this electron here, and we are having X-ray photons coming from this, and they collide, they strike. As a result, the electron is scattered, and look at this photon. This is the basic idea of Compton effect. We are having two wavelengths. One, the previous wavelength lambda, and we are having another new wavelength coming up, that is lambda dash. So, in Compton effect, electron is scattered by X-ray photons. As a result, we get two wavelengths, one lambda, that is called unmodified wavelength, and one is lambda dash, that is the modified wavelength. And this modified wavelength lambda dash is greater than lambda, and this difference lambda dash minus lambda delta lambda, this difference is called Compton shift. So, I repeat, in Compton effect, an electron is scattered by an X-ray photon. So, two wavelengths we get, one is unmodified wavelength lambda, one is the new wavelength modified wavelength lambda dash. Lambda dash happens to be greater than lambda, and this difference lambda dash minus lambda is called Compton shift. And this whole scattering effect is called very famous Compton scattering. This shift is Compton shift, and the whole scattering effect is called Compton effect. Now, the physics of this Compton effect is to look at the variation of Compton shift with the angle of scattering, and we will prove that the Compton shift increases with the angle of scattering. That is the job of this, and we have some graphical representation as well and some applications as well. Now, come back to this. We are having an electron which is stationary, static. You can compare it with the carom dot, and we are having an X-ray photon of wavelength lambda and frequency nu. You think of it as the striker of the carom board. You are striking this, and the X-ray photons are striking the electron, and as a result there is a scattering. Look at the scattering. In this scattering, this way we are having a new wavelength lambda dash, frequency nu dash for this photon, and this electron or the dot is going to one of the corner pockets with a momentum p. Before collision the dot was at rest, so its momentum was 0. After collision, post collision, its momentum is p. Before collision the wavelength was lambda, frequency was nu for the photon, and after collision, post collision, the frequency is nu dash and the wavelength is lambda dash. So, looking at this particular idea, and we will discuss or we will suppress, we will forbid a bit of relativistic effects here, because we are not going to not much calculating the relativistic effect. We will ignore the relativistic effect or Einstein's theory of relativity. We will think of this collision as forbidding the effect. Now, think of this same picture is here. Now, we are having the electron scattered by the X-ray photons, and X-ray photons, we are having a new photon, and that wavelength is lambda, new wavelength lambda dash, and the difference is Compton shift. Now, we will apply this particular two laws, two conservation principles. All of you are very acquainted with conservation of linear momentum and conservation of energy. So, let us find out some aspects of some parameters before collision and after collision for these two particles involved in this scattering or collision process. Come to this, before collision, after collision, go to energy of photon before collision. Energy of photon before collision is h nu, because all of you know Planck's quantum theory, energy of light is h nu. And after collision, we are having the new frequency nu dash. So, post collision the energy of photon is h nu dash. Momentum of photon before collision h nu by c, when energy is h nu upon c is the momentum, and after collision the momentum is h nu dash by c for the photon. Now, let us find out the same parameters for the electron. Energy of electron is m c square, but I am writing here as m 0 c square. What is m 0? M 0 is called the rest mass of the electron, and after collision this is a striking feature you have. The energy of the electron after collision is m c square. So, carefully mark, there is a change in mass. So, we are implementing, or according to Einstein's theory of relativity, mass is also a changing factor when the objects are travelling with much high velocity. So, due to that high velocity there is a change in mass. So, we distinguish these two. This is m 0, the rest mass of the electron. Before collision the electron was at rest, and after collision the electron is moving with a greater velocity. Atomic and subatomic particles, mass is very less and change in mass is evident. So, this m is a changing mass and we call it as the relativistic mass of the electron. Momentum of electron, as I told, it is 0 before collision because it was at rest, and after collision it is scattered with a linear momentum of p. So, now we will be applying two conservation principles, conservation of energy and conservation of linear momentum. If we apply conservation of energy principle, by applying conservation of energy, energy before collision, energy of photon is h nu, energy of electron is m naught c square. So, energy before collision is h nu plus m 0 c square, and after collision energy is h nu dash and the energy of the electron is m c square. So, it is h nu dash plus m c square. So, this is written according to law of conservation of energy. Total energy before collision is equal to total energy after collision. So, that is one of the equations from this particular table. Now, let us apply law of conservation of linear momentum before collision. But one important thing about momentum, energy we can add as numbers because energy is a scalar quantity. But when you think of taking care of momentum, you have to think of the vector addition. So, here this is the momentum, and imagine two mutually perpendicular axes to find out the rectangular coordinates. If this is the momentum, this component is p cos phi, this component of momentum is p sin phi. This momentum is h nu dash by c. So, this component is h nu dash by c cos theta, it is attached to the angle cosine. So, here this is h nu dash by c sin theta. So, when you think of adding the momentum, linear momentum before collision and after collision, you have to think of two axes, one x axis coordinate, one is y axis coordinate. So, look at the before collision the momentum of photon is h nu by c plus 0, because along x axis the electron was at rest before collision. So, the momentum is 0 is equal to, now think of the x axis coordinates of momentum of electron and photon. So, this is p cos phi and h nu dash by c cos theta. So, we get h nu dash by c cos theta p cos phi. So, that x axis component is over. Now, come to adding the y axis components before collision and after collision. Carefully mark, before collision the photon was travelling along x axis only and the electron was at rest. So, this vertical component or y axis component of momentum before collision is 0 for both, and after collision it is h nu dash by c sin theta p sin phi. But look at this, h nu dash by c sin theta is up, vertically up, p sin phi is vertically down, negative x axis, one is positive x axis. So, this is minus. So, this minus this. So, these three equations are now established looking at the parameters before collision and the parameters after collision by applying two conservation principles. One is conservation of linear momentum and other is conservation of energy. So, these three equations we establish, and without thinking much, without using much mathematical solutions, we just directly write down the results. So, by solving these three equations, no need to solve it now, by just solving these equations we get lambda dash minus lambda, we get lambda dash minus lambda is equal to h by m0 c 1 minus cos theta. This is one of the important conclusions driven by solving these three equations. So, here we get this is more significant. Now, we are focusing on this lambda dash minus lambda is our delta lambda. So, the same thing is going on, taking care of conservation of momentum and conservation of energy. Now, this delta lambda is h by m0 c 1 minus cos theta. So, now we come back to this is our Compton shift. This Compton shift, that was the target at the beginning. This is the relationship of Compton shift with the angle of scattering theta. We want to know this variation. How does it depend on, how does Compton shift depend on angle of scattering? Delta lambda is h by m0 c, that becomes a constant. H you know Planck's constant, m0 is rest mass of electron, c is the speed of light. We take it another constant lambda c 1 minus cos theta. This lambda c is h by m0 c, that is 0.0242 angstrom units, and this has a name called Compton wavelength. This is Compton wavelength. So, it has a value, fixed value. So, this is the result on which we are focusing on. So, Compton shift is lambda c 1 minus cos theta. Now, look at the variation. Theta, if I increase the value of theta, cos theta will decrease, all of you know that very much. Increasing the angle, cos theta decreases. So, 1 minus cos theta, this result 1 minus a small quantity becomes a greater quantity. So, I repeat, by increasing theta, cos theta decreases, 1 minus this small quantity leads to a greater quantity. So, look at this increase in Compton shift with increase in angle, look at this. So, there is an increase in theta and there is an increase in wavelength or Compton shift. So, this is the relationship between these two. So, our Compton shift increases with increase in angle of scattering. And to look at this graphical representation, by changing the values of theta, if I take this intensity versus shift or angle, if there is no scattering, 0 means just one dimensional. So, you find there is no shift at all, there is no shift. And if I increase theta 2, there is a shift of delta lambda, this one 0, and if I increase the angle to 45 degree, you find there is a little more shift. So, come to this picture, second picture. When I go for an angle of 45 degree, there is an increase in the wavelength or there is an increase in the shift delta lambda. Come to the third picture, when I increase the angle to 90 degree, you find one smaller peak and one greater peak. The smaller peak is our lambda on modified wavelength and the greater peak is lambda dash modified wavelength, and look at the difference between them. You find the two peaks are separated by a greater more distance. So, the Compton shift is increasing. And come to the fourth plot. In fourth plot, you find by increasing the scattering angle to 135 degree, you find these two peaks are separated much. So, what I want to prove that our Compton shift increases with angle of scattering, and finally, angle of scattering is maximum for 180 degree. So, this delta lambda is maximum, it is max for angle 180 degree. For the scattering angle 180 degree, delta lambda has the highest value. So, this is the idea of Compton effect. Just to take a brief note of the today's discussion, Compton effect, first point 1, Compton effect explains particle nature of light. Second, Compton effect is a scattering effect, is a collision between two particles. And what are the two particles here? X-ray photons and electron. Third point, most important, Compton shift, the difference between the two wavelengths. After Compton shift, you find lambda dash, before it was lambda, and this difference delta lambda is a function of angle of scattering, that is the physics of it. This change in wavelength, Compton shift, is a function of angle of scattering. And how does it depend? It depends directly. By increasing the angle of scattering, there is increase in Compton shift, increase in delta lambda. And finally, you find the result, and we are applying conservation of linear momentum, conservation of energy, and we are forbidding, not discussing much about relativistic effects, because in the theory of relativity, you know everything is a variable, time varies, length varies, mass also varies. So, I am not going much to that mathematics of relativity. And as a concluding part, we proved that the Compton shift is maximum for angle of scattering 180 degree. And to get one of its applications, or as a numerical you can think of, what we can do, people usually ask questions, why X-ray photons, that I was talking about the beginning, why X-ray photons are suitable? Do you have Compton effect for visible light? For this visible light, is Compton effect evident? Yes, it is evident. Compton effect, photoelectric effect, all they occur for all lights, but to get a visible effect, to get a striking effect, to get an experimental result, X-ray photons are suitable. But let us find out the answer to the question, do we have Compton effect for visible light? Yes, come to visible light ranging from 4000 angstrom units to 7000 angstrom units wavelength. This is violet, this is red. Let us find out Compton effect for violet, the minimum wavelength, and Compton effect for maximum wavelength. The change in wavelength by original wavelength into 100% is the percent shift. So, delta lambda by lambda, if we calculate it for violet, you find the shift is going to be from this formula, lambda c into 1 minus cos theta. Theta is maximum, the value of theta is maximum, lambda c into 1 minus cos theta, theta is 180 degree, and dividing it by lambda for 4000 angstrom units, 4000 angstrom units, you will find for violet this Compton shift is there, but it is, look at the value, 0.001%. By putting these values, you find delta lambda is coming out to be this 1 minus cos theta, lambda c is 0.0242, 1 minus cos 180 minus 1 minus 1 by 4000 angstrom units into 100%, it leads to 0.001%. So, for violet, Compton shift is there very much, but Compton shift is 0.001%. Come to red. If you apply the same formula for red by changing the wavelength to 7000 angstrom, you will find this percent shift is for red is 0.0007%. Look at these two values. Is there any Compton effect, Compton shift for visible light? Yes, but look at the range. It is from 0.001 for violet to 0.0007 for red. So, Compton shift is there, but it is very minimum negligible. So, I think we have a very good discussion on Compton effect. So, thank you very much, and you can connect for any sort of doubt. Thank you.